In this problem, we are to calculate the rate constant at 35 degrees Celsius for the hydrolysis of sucrose given it's equal to 1 times 10 to the minus 3 molars to the minus 1 second to the minus 1 at 37 degrees Celsius. And here we're given an activation energy of 108 kilojoules per mole. So this is a direct application of the two-point Arrhenius equation, where remember this equation is going to be the ln of K2 divided by K1 is going to equal the energy of activation divided by R times 1 over T1 minus 1 over T2. So in this particular case, we can take the natural log of 1 times 10 to the minus 3 molar to the minus 1 second to the minus 1 divided by K1, which is what we're going to solve for, and that's going to equal the energy of activation, which is 108 kilojoules per mole, but our value for R, our constant R, is in joules per mole Kelvin. So I'm going to make this 108,000 joules per mole, and that's going to be divided by 8.314 joules per mole times Kelvin. This is multiplied by, and we need to convert our temperatures to Kelvin here, so it's going to be 1 over 308 Kelvin minus 1 over 310 Kelvin. To make this a little bit more convenient to get rid of the natural logs, we take E and raise them to this power. Okay, that's going to simplify a lot of things for us. These guys will drop out right here, and we'll have 1.0 times 10 to the minus 3 molar to the minus 1 second to the minus 1 divided by K1. Okay, that's going to equal E. And if we do the math here, 108,000 divided by 8.314 is going to be 12,990. This is going to have a units of Kelvin times 1 over 308K minus 1 over 310K is going to be 2.09 times 10 to the minus 5. And that's going to have a unit of Kelvin to the minus 1. So these guys right here are going to cancel out. So we have 1.0 times 10 to the minus 3 molar to the minus 1 second to the minus 1 divided by K1 is going to equal e to the 0.272. If we rearrange this expression, we can say that K1 is going to equal 1.0 times 10 to the minus 3 molar to the minus 1 second to the minus 1 divided by 1.31, which is e to the 0.272. And this will tell us that K1, or our rate constant, is going to be 7.63 times 10 to the minus 4, and it's going to have units of molar to the minus 1 second to the minus 1. So in this particular equation, and I guess I should have put 1.0 up here for our initial rate constant, which means this is going to have two significant figures, so we should represent this as 7.6 times 10 to the minus 4. So let's think about if this particular answer made sense. We went through, we plugged everything in. This equation can get confusing sometimes, and we might flip the K1 and the K2. But if you think about it for a second, if we have a value of 1.0 times 10 to the minus 3 for our rate constant at 37 degrees Celsius, when we go to a cooler temperature, we expect K to decrease. And in fact, it did here, because we went from 1.0 times 10 to the minus 3 to a smaller number, which is 7.6 times 10 to the minus 4. So this answer for this rate constant indeed does make sense based on the theories that we were talking about, and we can report that as 7.6 times 10 to the minus 4. So this is how you apply the Arrhenius equation to solve for a particular case, and in these example problems we can solve for any one of these variables in here, whether it be K1, K2, T1, T2, or the energy of activation.